this because I got 3 people absent today, is an easy way for you to be able to remember what are all the things I need to be able to graph a rational function. Now, by rational function, what do I mean? I mean it's going to be some sort of a fraction. Okay? For example, we might be graphing f of x is equal to 2x plus 1 over 3x squared minus 2x plus 2. That's a rational function. You see what I'm saying? It's got a numerator and a denominator, and both of them have polynomials in them. Okay? You don't have to write down that example. I just am showing you that's what a rational function is. You'll get plenty of examples in just a little bit. So what does rady stand for? R in rady is roots and removable discontinuities. Thank you. Connor, Jalen, Braylon. Just your reminder for inductions. Come on, get them. Roots and removable discontinuities. Okay, that's R. In other words, why do I need to know that? I need to know where it crosses the x-axis, right? That's a major landmark. That's the roots. Removable discontinuities would be holes in the function. I need to know if they're holes in the function. Okay? So these are going to be my x-intercepts, and these are going to be holes. A is vertical asymptotes. Why is that important? Because what does the function do at a vertical asymptote? It goes to infinity or negative infinity, doesn't it? These are things that happen in the middle of the function where we have discontinuities. All right, T is what we call tangency and togetherness. Guys, this has to do with multiplicity, doesn't it? We've seen that word tangent before. So where we have a multiplicity of a factor or a 0, we need to know, does it touch the x-axis there or does it pass through? Okay? You see what I'm saying? That helps us describe what the graph is doing. Togetherness has to do with the vertical asymptotes. In other words, do both ends go up around the vertical asymptote? Do both ends go down? That would be togetherness. Or does one end go up while the other one goes down? That would not be togetherness. So they either have togetherness or they don't. But that tells us what our function's doing around the vertical asymptote. Okay, so is everybody good with togetherness and tangency? Does it touch or pass through the x-axis? What does it do around our vertical asymptotes? E is for end behavior. And guys, this is my horizontal asymptotes. Does it have any? Does it have horizontal asymptotes? Does it have slant asymptotes? Does it not have asymptotes? Because remember, horizontal asymptotes, or you're going to learn what slant asymptotes are, those tell us what it's doing if it's doing anything special at the ends, doesn't it? If it has a horizontal asymptote, it doesn't go to infinity and negative infinity. It goes to the asymptote, the ends. So those have to do with the end behavior. And then Y is the Y-intercept. In other words, does it cross the y-axis and where? If you know all of those things, you can graph this entire function. So, how do we use rady? You're going to be learned to just tick it off, R-A-T-E-Y, and find all the things and then put the things in the graph. Or find them and put them on the graph as you go. All right. So, step 1, simplify the function. What do we mean by simplify the function? We're going to factor everything. If we have a polynomial, we're going to factor the polynomials and get rid of any extraneous factors. Okay? What do extraneous factors mean? Anything that's the same in the top and the bottom, right? In the numerator and denominator, if we have the same factor, we can get rid of it, can't we? But if we do that, what happens? We know that gets rid of a removable discontinuity. Okay? So then we'll have to check and see, is that a hole? Because it may be a hole if it's removable, isn't it? So then we have to check and look at it. Step 2, employ Rady. It says put all the Rady features on the graph and draw it. So how do we do that? How do we do roots? And removable discontinuities. So roots. For roots, which is the big thing here, set the numerator equal to 0 and solve, right? Numerator only. Does it say set the whole thing equal to 0? Set the top of the function equal to 0 and solve. That's where your x's are going to be. Anyway, those go to 0. Think about it. If one of those factors goes to 0, then doesn't the entire thing go to 0? Isn't 0 divided by anything 0? So do you see how we only have to deal with the top? Okay. Solutions are your roots, which means those are places where it crosses the x-axis, aren't they? Those are our x-intercepts. Removable discontinuities has to do with this guy right here. Now, if we have any factors that are removable discontinuities, in other words, if we had any factors in the top or the bottom, any common factors that disappeared, we have to figure out what the value is close to that on either side. Okay? You see what I'm saying? That way we know where to draw a hole in the factor. All right? So basically what we do is we plug in back into the function. Once it's gone, we plug back into the function where that 0 would have been, where that hole would have been. Okay? So let's say we had, and I'll show you this as we go, but let's say we had x minus 3 that disappeared. We would get rid of the x minus 3, and then we would plug 3 back in to see what value we get. And whatever value we get on the graph, we put a hole there instead of putting a point. You'll see. A, asymptotes, vertical asymptotes. Specifically, vertical. Now what does it say? Set the what? Yeah, so for the roots, we got the numerator equal to 0. For the vertical asymptotes, we set the denominator equal to 0. Think about why that makes sense. If we have zeros in the denominator, that's a place where it's undefined, isn't it? Can we have 0 in the denominator? No. So that's why we check for those, and I feel like I'm yelling. I'm going to lose my voice by the end of the day. Hang on. Okay, that's better. Now I don't have to yell. All right, so vertical asymptotes. Set the denominator equal to 0. So we have to do that. It says test each one to see if it's a hole or vertical asymptote. How do we do that? You're going to plug in points, and take a look at this. It says plug in points extremely close to the discontinuity from both sides and see if it goes towards positive or negative infinity. Think about that. If it goes towards positive or negative infinity, it's an asymptote, isn't it? What if it doesn't go through positive or negative infinity? Then it's a hole. Then it's just a place, that one single place. So if it goes towards a specific number other than infinity on both sides, it's a hole, and you figure out where the hole is. Read what I said earlier. Okay? So is anybody confused so far? I'm going to go through all the steps, and then we're going to do a bunch of examples, and you'll get the entire process. All right. T. T was for what? Yep. Tangency, togetherness. Everybody always remembers the tangency and never remembers the togetherness. And they're always like, what does that mean? I don't remember. I don't understand. All right. Look what it says. It says right here, check the powers of the factors in the, for tangency, it's the numerator, isn't it? If the powers are even, then the graph does what? Touches and bounces off, doesn't it? It has tangency. We learned this. If it's odd, what do we know? Passes through. It intersects, doesn't it? You already know this stuff, guys. We're just putting it all together. Now, for togetherness. Togetherness means how does it act on both sides? Do you know how we figure that out? We're just going to have to plug in a couple of points and see, okay? Do they both head towards infinity and negative infinity on either side, or does one go up while the other goes down? A lot of times when you start putting in things like the Y-intercept and the x's and stuff, you'll be able to tell what's happening, okay, on both sides. If you don't, then you just have to plug in a couple of points close to the asymptote and see, okay? If you have a vertical asymptote at x equals 2, you can plug in 2.1 and see, is it going way up or is it going way down? You can plug in 1.9 on the other side of 2 and see, is that going up or is that going down? Do you see what I'm saying? So you can plug in points if you're not sure and see what the graph is doing on either side. All right? All right, so what does it say? It says check the factors for togetherness. We check where? If the power is even, the function acts the same. If the power is odd, the function acts in opposite directions. So even will tell me either both go up or both go down. Odd will tell me that they go in opposite directions. So if you can figure out, if you've got an odd power on something, in other words, you've got a multiplicity of like 3 in the denominator on one of those roots, or on one of those vertical asymptotes, then you know it's going to do this or this. Well, if you plug in on one side and it does this, then you automatically know what the other side does, don't you? Because it's going to go in the opposite direction. Let's say instead it has a multiplicity of 2. If you plug in on one side and it does this, then you know automatically the other side also does that because it's even and it has togetherness. Get it? Is everybody kind of getting the idea? All right. So E, end behavior. End behavior is the hardest one and the one everybody messes up the most. Believe it or not. You have to test to see if you have horizontal or oblique asymptotes. And by oblique, we also call them slant, because oblique means sort of sideways. Slant means the asymptote is a straight line or a curve even sometimes. It's not typically horizontal. Did you know you could have other types of asymptotes other than vertical and horizontal? You could have a diagonal line. It just means that the ends go that way instead of going straight down and across, okay? So how do we know? This is where lead powers, lead terms come into play, okay? This has everything to do with lead terms. You're going to check the power on the lead terms, okay? So we're going to look at the lead term here on the top and the lead term in the bottom. And we're going to look at, now I'm going to make this bigger so you can see it. Do you see those? We want to know whether or not that one is, the top is smaller power, the same power, or a bigger power. If the power in the top is smaller, in other words, numerator power is less than denominator power. Guys, an example of that would be if we had 2x squared over 3x cubed. Do you see what I'm saying? If n is less than m, we have a horizontal asymptote. And it is at x equals 0. Think about why it would be at x equals 0. If the bottom power is bigger than the top power, that means the bottom is growing faster than the top is, isn't it? So as we get bigger and bigger and bigger numbers, this guy being bigger, more power than this one means that the bottom gets bigger and bigger and bigger and bigger and bigger faster than the top does. Well, if the bottom gets bigger in that fraction, what is that fraction going towards? 0. Think of it as 2 over 10, 2 over 100, 2 over 1,000, 2 over 1,000,000, 2 over 1,000,000,000. What is that number going towards? Big fat 0, isn't it? So do you see why the horizontal asymptote is the x-axis. It's x equals 0, right? I'm sorry, why am I saying x equals 0? Y equals 0. Duh. Horizontal asymptote would be y equal, wouldn't it? And not one of you said a word. Were you thinking it? Say something. All right, so does everybody understand why if the bottom is bigger than the top, that it's y equals 0, it's the x-axis is the horizontal asymptote? All right, so what if they're equal? We still have a horizontal asymptote, guys. Difference is if they're the same power, we strip off the coefficients in front. Okay? So if we have that, then what we have is if we have ax to the n over, let's say a to the n, x to the n over a to the m, x to the m. If these are the same, then our horizontal asymptote is y equals a to the n over a to the m. In other words, we pull, those x's are going to go away, aren't they? Think about it. It's just the coefficients in front. Yes, it is just the coefficients in front. So for example, if you had 2x squared over 3x squared, that would mean the horizontal asymptote would be at y equals 2/3. Get it? Is anybody confused? Now, here's for the big ugly. This is the one nobody likes. What happens if the top exponent is bigger than the bottom exponent? This means we do not have a horizontal asymptote. We have an oblique asymptote. We have a slant asymptote. Okay? No horizontal asymptote. It's a slant or oblique. And see oblique asymptotes here. Because this is why nobody likes them. Finish writing that down and we'll go over how do you find said slant asymptote. It's most of the time going to be a line, okay? It can be a parabola, believe it or not. We could have a parabolic asymptote. We could have a cubic asymptote. Typically it's one bigger though, is the ones we deal with, and that means it's a straight line. Think about why it would be a straight line. If you take a cubic and divide it by a quadratic, what's going to be left? X to the third divided by x to the second means you're just left with x, and that's linear, isn't it? Isn't that a line? X. That means that our asymptote is going to be a slanted line. That's why it's called a slant asymptote, all right? So if it is 1 degree higher, if n is exactly 1 degree higher, then you have an oblique asymptote, and it will look like a diagonal dashed line on your graph. Why dashed? Indicating that it's not really there, right? We would actually not really put usually the actual asymptotes on there. We would put them on there and we would erase them off but I want to see them on there because you need to see them on there. Now, how do we find the equation for this line? This is why nobody likes it. Polynomial long division. But here's the nice thing. You only have to do enough polynomial long division until you get the equation of the line. What does it say right here? Throw away any remainder. We don't care about that. Because all we're looking for is the equation of the line, aren't we? And that would not include the remainder. We're just looking for the x and the b, right? mx and b. All right. So last but not least, we've got y, which is the y-intercept. How do we find the y-intercept? Yeah. Y-intercept is f of 0, isn't it? So we just plug in 0 for x and we solve for y. Typically, you know what that's going to be? That's going to be the constant of both terms at the end, isn't it? Because all the other x terms are going to do what? Go away. So you can plug in all you want, but if you're smart about it and you realize that all the x's disappear, all you get left is what's not got an x next to it in the top and the bottom, and that tells you where your y-intercept is. All right, So are you guys ready to try some? What do you think? I think we are. So let's start with example uno. Example 1. Look at this lovely. Now, I've been really nice to you in example 1, and it's already what? It's already factored. So the first thing we have to check, it's almost all the way factored. It's not quite all the way factored. What could we still do? I could pull out a 3, but it's not a huge deal if you don't. So, because it'll go away in the wash anyway. All right, so let's start looking at this. First things first, do we have any factors that are mutual? In other words, do we have any extraneous factors that will disappear, that will cross out? So we have no extraneous factors, do we? All right, so let's start with rady, which is, and that's the first thing I always write is, no extraneous factors. So what does that mean? That means I'm not going to have any what? I'm not going to have any removables. I'm not going to have any holes, am I? Okay, so here we go. So R is for roots. And what does it say for roots? Take the what? Top factors equal to 0, which means we have 3x minus 3 equals 0, and solve for x. We get x equals 1, and we get x equals what? -4. So we have roots at -4 and 1. Now, here's the cool thing. We can go ahead and put those on our graph, can't we? At -4 and at 1. Now, we can already go ahead and talk, since we're looking at these, we can talk about tangency, can't we? And I recommend you do this as you go through the top. Are either one of these got a multiplicity? So do we have any tangency? No. So we write none. In other words, it intersects both at -4 and at 1, doesn't it? So what do you think? Oh. You are awesome. You've already got them all signed?
And Ms. Lopez put the names on it.
Thank you. Thank you, thank you. She's awesome. All right, so it's going to go through in both of those places, isn't it? They're up or down. All right, so let's move on to the next one. A. What are we checking for in A? Vertical asymptotes. All right, so vertical asymptotes. So what are we going to do for vertical asymptotes? Whatever the factor is in the bottom, which is x plus 2 equals 0, isn't it? All right. So where do we have a vertical asymptote? X equals -2. All right, so let's go ahead and put that on the graph as well. So a dashed line vertically right here. Now, this is where we talk about togetherness as well, isn't it? So, togetherness. Does this thing have togetherness or not? How do we tell? Remember, we're looking at this right here, aren't we? Is it even or odd? It's even, so does it have togetherness? Yes. We just don't know which way yet, do we? So we know both ends go in the same direction, right? So that's either going to be, it's either going to go this way or it's going to go this way. Does everybody understand that? And we'll figure out which way that is in just a few minutes. Once we have a few more points on our graph, we might be able to tell. All right, so now, let's keep going. E, end behavior. Now here's the fun part of end behavior. This one sucks when it's already factored, doesn't it? All you have to do is take the lead term of each thing and multiply them back together. So we've got what? 3x times x in the top, right? So that's 3x squared, and what do we have in the bottom? X squared in the bottom, right? So we have 3x squared and x squared. So what do we notice about these two right here? They are the same. So that is the n equals m case. So do we have a horizontal asymptote? Here, hold on a second. Let me flip this around so I can see some of you going, all right, is that better? Okay. So we have a horizontal asymptote, don't we? At y equals what? Yeah, this is the case where if they're equal, we just strip off the coefficients, don't we? So what's the coefficient on the top? 3. What's the coefficient on the bottom? 1. So 3. So we have a horizontal asymptote at y equals 3. So let's put that on. Now, remember horizontal asymptotes. Do horizontal asymptotes have anything to do with the middle of the graph? Can the graph cross the horizontal asymptotes? Yes. It only means the ends go towards 3, doesn't it? Isn't that what it means? All right, so let's finish this up and see if we can figure out Y-intercept. So to find the Y-intercept, it's f of what? F of 0. Now in this case, again, we can't just figure out what it is at the end, can we? So let's just plug in zeros for all our x's. So we have 3 times 0 minus 3. We have 0 plus 4. And we have 0 plus 2 squared. So that goes away, that goes away, that goes away. So in the top, what do we have? In the numerator, we have what? Multiplying, we get negative 12 here. And in the bottom, what do we have in the denominator? 2 squared is 4. So my y-intercept is what? Negative 3. So we can go ahead and put that on our graph, can't we? Y-intercept is at negative 3. 1, 2, 3, right here. Now this is really nice because guess what? This tells me which direction it's going, doesn't it? I want you to think about what's happening. It's got to go this way, and there's a vertical asymptote here, which means it's got to keep going that way, doesn't it? Yes? Now on the other side, it goes up, but what is it going to go towards? The end behavior. There's nothing else for it to do, is there? Now, we've got one side done. It won't go up past the horizontal asymptote. It won't go past the vertical asymptote. Now, this is where togetherness comes into play. Did it have togetherness? So if you look back up here where it said togetherness, we said either the ends both went up or the ends both went down. Which case is this going to be? They both go down, don't they? So take a look at what power that gives you here. What does that mean? From here, it means this goes that way, and then it goes towards the horizontal asymptote on that side. You see how ratey gives you all the pieces you need to figure this out. What do you think so far? As long as you get, that's why I'm trying to give you this. I know it sounds stupid or ratey, whatever, but it gives you all the pieces to make sure you're organized and don't forget anything. So let's look at some additional examples. We're going to look at several more together, and then we'll look at you trying one on your own. All right. So, first things first, we have to do what? Factor. All right. 9 minus x cannot be factored, but x squared minus 4 can. What does it factor into? Do we have any extraneous? Good. That means we don't have to worry about what? Okay, so no. That means no holes. Those are the ones we don't have to worry about then. Cool. We will do an example where we have a hole, just so you know. The next one. All right, so now all we have to do is look at what? What's R? If we're not looking for removable, what else does it have to do with? So this is the no removable. So we're looking for roots here. So what do we say? Okay. So 9 minus x equals 0. Numerator equal to 0. Please solve for x. Negative x equals negative 9. You'd be surprised how many times people get this wrong. X equals 9. So we have a root at 9, don't we? Put it on your graph. Root at 9. Right here. Okay. A. Vertical asymptotes. Are we going to have a vertical asymptote? Yeah. How many? 2 turns out. 2 vertical asymptotes. X plus 2 equals 0. X minus 2 equals 0. Now, we're pretty sure we don't have any holes because we didn't have any extraneous factors, but you're going to find something weird happen here. What does it say under A for asymptotes? You must do what? Oh, gosh. We got to test each one? Really? Yeah. You're going to see why. We have to test each one. Did you know we could have a hole even if we don't have a removable? Did you know that? Oh, so I'm going to make myself a liar and say, really? We don't have any removable, but we might have a hole. Now, let's test and see. So how do we test? What do we do? We got to test points close to each one. Believe it or not. So we've got what? X equals negative 2 here, and x equals positive 2 here. How do we do that? We got to plug in a point and see what we get. That means you got to get a graphing calculator out and look at plugging into that function. It's not that bad. And no, you're not going to use it to graph. You're just going to use it to check the So now, what are we going to test here? We got to test both of these, don't we? So, let's test the negative one first. So what's a point really close to negative 2? Nah, that's not really close. What's a point really close to negative 2? Negative 1.999. So plug in x equals negative 1.999 and see. That's my husband. Who it is? How'd your test go, sweetheart? Okay, so how do we do that? 9 minus negative 1.999 divided by, in parentheses, negative 1.999 plus 2. And then we can divide again. Oh, I'm seeing a pattern here. Negative 1.999 minus 2. Oh, I'm getting a really big number. Anybody else getting a really big number? Negative 2,750? Okay. So y equals negative 2,750. So is this a whole? What is this telling me it's doing? As we get really close, it got really negative, didn't it? So is negative 2 a vertical asymptote? Yes, it is. As a matter of fact, at negative 2, we can just make ourselves a sketch here. So at negative 2, it's going to go, which side is negative 1.99999 on? The right side or the left side? It's on the right side, isn't it? So we know on this side it's going to go this way. Now, I want you to think about this guy. Remember togetherness? Do we remember togetherness? We have to check each of these for togetherness. Do these guys have togetherness? Do either of them have togetherness? This is to the first power. This is to the first power, isn't it? Do you know the mistake people make? They look right here and they go, well, they're squared. No, it has to do with multiplicity. Is that squared the multiplicity? No, it's on the outside of the factor group, isn't it? So this would be a big no-no. Don't do that. So these both have a multiplicity of 1. It's odd, isn't it? So do either of them have multiplicity? Do either of them have togetherness? No. So neither one of them have togetherness. So that's a no. So what is this guy going to do on the other side of the asymptote? If the right side goes down, the other side's got to go up. So now all of a sudden we've got a sketch to help us. Yay, don't we? You see how this helps, knowing all this? Now we got to check x equals 2. So give me a point very, very close to what? Negative 2, to positive 2, right? 1.99999? Okay. Let's try x equals 1.999. All right. So plug that in. 9 minus 1.999 divided by 1.999 plus 2 divided by 1.999 minus 2. Oh, that gives me y equals what? Wow. Negative 1,750. So what did that tell me after all? Is that a vertical asymptote? Turns out, yeah, it is also a vertical asymptote. So this is at 2. Which direction is it going though? This is still helping us, isn't it? What direction is it going? 1.999 is on which side of it? The left. And in the left, it's going down. Does it have togetherness? So on the right, it's going up. Okay, let's remember that. So we do have 2 vertical asymptotes. What? But you said we didn't. If you're not sure, check. You see, it's not that hard. Did it take that long to check it? No, didn't take that long to check it. So let's put those in. Oh, hey, did we put, and we've got our 0, don't we? On there. All right, so what do we do next? Ooh, tangency. Let's go to tangency. Tangency has to do with what? Numerator. So this is to what power up here? This is to the first power, isn't it? So does it have tangency? No. It's going to intersect, isn't it? So tangency is no. So it is going to cross through that point. So no tangency. So now let's get the other things that we need to graph this thing. And behavior. So horizontal asymptotes. This one's nice though, because at least what? What's the lead coefficient in this guy in the numerator? Not just x, negative x, right? So in the top we have negative x, and in the bottom we have what? Yeah, go back to what we started with down here, which is x squared is our lead term, isn't it? So we got x squared and we got negative x, so x squared. So this is x to the first, that's x squared. So n is what? This guy's n, this guy is m, isn't it? N is less than m. In other words, the top is less than the bottom, isn't it? So if you got rid of an x, it would be 1 over x, wouldn't it? Which is going to go towards what? 0. So since n is less than m, we have a horizontal asymptote at y equals 0, don't we? Let's put that on our graph. Anybody confused? So y equals 0 is the x-axis. But, Miss Duffy, I'm confused. I have a point on the x-axis, but I have a horizontal asymptote on the x-axis. I did something wrong. No, you didn't. What did I say?
You can go through it.
You can go through it. As a matter of fact, you know how you know you're going to go through it? Because you got a point on it. Otherwise, you're not going to go through it. Okay? Does everybody get that? Don't freak out if you end up with a point on the horizontal asymptote. It just means that it goes either up and down, up through it and back down, or it goes down through it and, it's going to go up through it and back towards the asymptote, or down through it and back towards the asymptote. It's going to do a little weird wiggle thing. Okay? You'll see it. What's the last thing we need to find here? Y-intercept. So f of 0 is what? This is the nice thing, guys. This is what I'm talking about. If we have, let me put it over here. If we have 9 minus x and x squared minus, or it was x squared minus 4, if we plug in a 0, what's going to go away? All of the x's are going to go away, aren't they? So what's left? 9 over negative 4. So 9 over negative 4. So negative 9/4, which is what point? Negative 2.25. So my y-intercept is at negative 2.25, isn't it? And yes, you can put negative 2.25 on a graph. Negative 2.25 right here. Holy smokes. This is bizarre, isn't it? So,
That's the top of the graph.
that's probably the top or the bottom of a parabola. We don't know which, do we? Or do we? Because of the tangent, the togetherness thing, right? So let's look at our togetherness thing. What did it say it's doing in between negative 2 and 2 here? It's going which way? Downward, isn't it? That means that in between right here, from here it's going down. Boom. Now, did it have togetherness? No. Which means that the other two sides of those asymptotes are doing what? Which means on this side, it has to be going up this way. Now, does this have a point out here somewhere? Is it going to cross this asymptote then? No. Which means this side just goes this way. Now, let's look at the other side though. On this side, we know it's going upwards, don't we? But what do we have right there? A point, which means it's going to do what? It's going to cross it, isn't it? Because it's not tangent. It's going to cross it, and then it's going to have to do what? Go back up towards the asymptote, isn't it? So from here, it's going to go up. That's what the togetherness told me. And then it's going to come down and then eventually go back towards the asymptote. kind of cool if you think about it. All right? But we got that graph. That's a pretty complicated graph, isn't it? But we got all of that, being, right from Rady. Let's do one more together, example 3, and then I'm going to let you try some on your own. We got another one, example 4. I'm going to let you go through all of the fun stuff on your own. Because 3 is ugly. If you can get through 3, you can get through anything. Because 3 has all kinds of fun stuff. Okay, number 1. 3 has that guy. If we're going to be able to factor that, what do you suppose it's got to be? It's probably got to be the difference of 2 cubes or something. We don't know. How do I factor that? What? P over Q's. Guys, you're going to have to do P over Q's if you don't know how to do it otherwise. Are you serious, Miss Steffi? Am I going to have to do all that crap too? Yes, you are. So, this, you're going to have to do P over Q's and find a factor, aren't you? If you don't have a calculator, then you've got to do it the old-fashioned way, don't you? Yeah, that's gonna be ugly, isn't it? All right, so let's factor this thing. What are my P over Q's going to be? Plus or minus what? Plus or minus 1, right? Plus or minus 2. Oh, plus or minus 2. Plus or minus 3. Plus or minus 4. Plus or minus 6. And plus or minus 12. Descartes' rule of signs. How many sign changes do we have? 1 positive, right? So we know there is 1 positive real root. So let's figure out what that 1 positive real root is. Yeah? Because if we can find the 1, then it's a quadratic, isn't it? And then we can factor it. Sorry, guys. This is the way it goes. So let's go over here, and let's find a spot, and let's put this through. We've only got 1, 2, 3, 4, 5, 6 of them to check. Maybe we'll get lucky. Let's try 1. 1, 1, negative 8, negative 12. 1, 1, 2, 2. Negative 6, nope. Not 1. So let's try 2. 1, 1, negative 8, negative 12. Here we go. 1, 2, 3, 6. Negative 2, that's not going to work either, is it? So 2 didn't work. So let's go to 3. Lucky thing is they go pretty fast, don't they? 1, 3, 4, 12, 4. Oh! Ha-ha! Ta-da! Found it! And what is this? Quadratic. This is now x squared plus what? That will factor, won't it? X plus 2, x plus 2, right? All right, guys, so this factors to x minus 3. This is x plus 2 squared, isn't it? And yes, you do need to write it that way because we got to look at its multiplicity, and then we got x minus 6. Now, we need to figure out if we can factor that in the bottom. What is that quadratic in the bottom factor to? X minus 2, x plus 1, and then x minus what? 6. Oh, by the way, please, this is separate. I don't want you to think that's a multiplicity. Right? Don't make that mistake. All right, so now, what do we have to get rid of here? X minus 6. This is a removable factor, isn't it? Which means, guess what? We have a whole... So let's deal with our roots, and then let's deal with our whole, okay? The removable. Is anybody confused? Did I say this was going to be easy? This is why you're in advanced pre-cal. So you know how to do this. That's where the P over Q's come in. Did you think you were going to learn P over Q's and then never have to use them again? You were hoping. Sorry. All right, so here we go. Let's do roots. All right, for roots, what do I set? X minus 3 equals 0. X plus 2 equals 0. Do I do the x minus 6 equals 0? No, I got rid of it. Chucked it. So what are my zeros? X equals 3, x equals negative 2, right? So let's put those in the graph. X is negative 2. X is 3. Yay. All right. So let's go up here and figure out where our removable is. What is our hole? How do I figure out what it is? Where it's at? We take the 6 and we plug it back into what's left right here. So we take f of 6. You know why it's 6? Because that's what x equals at that point, right? And we plug it back into what's left. We don't plug it in the original. We got rid of the x minus 6. So we have to do 6 minus 3. 6 plus 2 squared. 6 minus 2. 6 plus 1. So this is 3. 8 squared is 64. 4 and 7. So 3 times 64 divided by 28. 6.9. So I have a hole at the point 6, 6.9. And you know what I'm going to do? I'm going to put that on my graph. Is anybody confused about what I did? Did you follow it? We take the x that makes the hole that we removed and we plug it back into what's left to find the point. So put the point 6, 6.9 on your graph. So that would be over 1, 2, 3, 4, 5, 6 up 1, 2, 3, 4, 5, 6, almost to 7, and we've got a hole right there, don't we? Hang on. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. It's almost to 7, isn't it? Notice I'm making an open circle, not closed, open. There's my hole. Is everybody good? Okay, so let's keep going. While we're at it and we're looking at the roots, maybe we ought to look at tangency. Do you see how it kind of goes together? Do we have any tangency? Yeah, we do, don't we? Look at the numerator. Tangency, yes, at x equals negative 2, and no at x equals 3, right? Does that make sense to everybody? Yes? No? Thumbs up? Yeah, because I can't see your face. Okay, why? Look, you've got tangency, remember, has to do with whether it's an even, the multiplicity. We've got an even multiplicity here. That's this root, which means it's tangent at that root. It means it's going to touch there. This is a multiplicity of 1, which means it's odd, which means it's just going to pass through. Okay? All right. Now, while we're here, let's do vertical asymptotes. Vertical asymptotes. What are we going to set equal to 0 now? Yep. X minus 2 equals 0. X plus 1 equals 0. So x equals what? X equals negative 1, doesn't it? Those are our vertical asymptotes. Now, we'll deal with togetherness in just a second. Let's go ahead and put those on. So we have a vertical asymptote at 2 and a vertical asymptote at negative 1.
So why did we do, like, which one's closest to 2 on the last one, but on the left?
Because we know where the hole is.
There could be multiple.
Nah. If you've got a removable, then you've got a hole. If you don't have a removable, you don't have a whole. All honesty. At least in the problems we'll be doing, that's how you know. If you've got a removable, then you need to check it. Now, if you want to go ahead and check on either side of it, just to make sure, then you'll know which way your togetherness, which way your ends are going, won't you? It's an easy way to check it, isn't it? You may have to go back and do that anyway, based on what? How many points you have and whether or not you got enough to do it. Okay, so here we go. Togetherness. Do we have togetherness? Look at the powers on the factor groups. Do we have any multiplicity other than 1 on any of the factors in the denominator?
No.
So do we have togetherness? No. There is no togetherness on either of them. Which means they're both going to do what? Opposite ways, right? So they're both going to go opposite. So we can figure it out. Okay. Now, if we have to, we'll come back and explore that, because if we can get it without having to plug in close, we can. All right? So, E, end behavior. What is my lead coefficient? We base it on what's left. We got rid of a factor, so that doesn't count, does it? It doesn't matter. We could still do it to the original. What is my term going to be? What's my top term going to be here? X to the what? Fourth. And what's my lead term going to be here if I multiply this together? So this is X to the fourth, and this is X to the third, isn't it? So, now, because we got rid of this, we could just look at x cubed and x squared, couldn't we? Matter of fact, that's just as easy. If you can get rid of a factor, you can look at what's left to see. So we got x cubed and x squared, right? So for horizontal asymptotes, we have x cubed over x squared. This is my n, this is my m. So what do we know about the relationship between n and m? N is greater than m. Not only is it greater than m, it's greater than m by what? Exactly 1 degree. If it's bigger by 1 degree, it means it's what kind of, do we have a horizontal asymptote though? Horizontal asymptote is no, we have a oblique or a slant asymptote. So guess what we have to do? We got to go down here and we got to find it. Okay? So we are going to take x cubed plus what? Where is this coming from? The original. What we had left after we got rid of our removable, right? So what goes on the outside? Yep, x squared minus x minus 2. What's left on the bottom? So now we do our division. Biggest divided by biggest, right? X cubed divided by x squared is what? X. Now multiply. X times x squared is x cubed. X times negative x is negative x squared. X times negative 2x is negative 2x. And we're going to do change the signs, aren't we? Boom. So x squared plus x squared is 2x squared. This is minus 6x minus 12. Now, here's the nice thing. You do not have to work this all the way through. Remember what I said, we're only looking for what? We're looking for the equation of the line, aren't we? So now I'm going to take biggest term divided by biggest term. And what is that? Positive 2. I can stop now. I don't even have to multiply it out. Why? Because this is the equation of the line, isn't it? So when you get back from lunch, we're going to finish this problem up and you're going to try one. You can do it. We were at this point where we had found our asymptote, right? So you just have to graph this guy. It has a y-intercept of 2 and a slope of 1, doesn't it? So y-intercept of 2, slope of 1. And look, it goes right through one of those points too, doesn't it? So I'm just going to make it a dashed line. And there's my slant asymptote. Okay? So now, we begin to put stuff together. Y-intercept is the last thing we need, isn't it? So let's do our y-intercept. F of 0, would you agree? So if we're doing f of 0, we got x cubed, what, plus x squared minus 8x minus 12 up here, because we got rid of the x to x minus 6. And we've got x squared minus x minus 2 in the bottom. Right? Now, why am I writing it this way? Because what's going to happen to all those x's when I plug in a 0? Goes, 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 goes. So what's left? Negative 12 over negative 2, which is 6. So I have a y-intercept of 6. So we're going to go up here. 1, 2, 3, 4, 5, 6, and we're going to put our y-intercept right here at 6. All right. So this is where we start to draw. You've got pretty much everything you need at this point, because what do I know? I've got to have 2 points that attach to start somewhere. Do you see where we've got 2 points that are in the same zone, so to speak? I got a hole, and then I've got this point, don't I? So we know it's going to go this way. And then this is going to go towards this asymptote, isn't it? Do you see that this is a good starting place for me, isn't it? Now, this is where the whole togetherness happens. Did this thing have togetherness? Let's go back up here. No, it didn't. So if it doesn't have togetherness, what do we know? If it goes down here, it must go up on the other side, which makes sense because we get this point right here in between, don't we? This side goes up. Okay. So now, can this function cross that vertical asymptote? No. So what happens to it on this side as we go to the left of this point? It also has to go up. Now, y'all, some of y'all are going to be like, but it doesn't have togetherness. Guys, togetherness is around the asymptote, not between the asymptote. Do you see the difference? This is saying it doesn't have togetherness. These two have nothing to do with each other. Do you see what I'm saying? On both sides of this would be no togetherness. On both sides of this would be no togetherness. So if this chunk goes up, then the other side has to go where? Down, which means it has to be down here somewhere, doesn't it? Why does it have to be down here somewhere? Or, oh, we got a point here though, don't we? Okay. So what happened at this point though? So is it above or below? Because we got a point right there. That point. Now we got to look at what? Tangency. Did we have a point that had tangency? Which one of those had tangency? The negative 2 did, didn't it? So it is going to touch at that point, and then it is going to what? Bounce, isn't it? Now, if this side goes up, then this side has to go down, touch here, and then go yet away, doesn't it? And that's what it looks like. Now, here's another question for you. How did I know, how did I know that this side had to go up? If it went down, well, it can pass across this asymptote in between. Remember, this asymptote only does end behavior. It can cross that. It would have crossed the x-axis. Is there a point for it to cross the x-axis in between here? No, there isn't, is there? So if it was going to go downward, it can't cross the y, it can't cross this vertical asymptote. It can cross the horizontal, it can't cross the vertical, can it? So if there's no place for it to cross on the x-axis right here, then it has to go up. And if that side went up, the other side had to go down, didn't it?
These to give out.
Okay, yes, go for it. Do you know who they are?
Joshua Hughes.
Josh? And guys, I know it says November, it should say January. Sorry. Addie. Yeah, Addie, yeah. Logan's not here, yeah.
Thank you.
Thank you. All right, guys. So any questions about this? So we had everything we needed. All right. So you get to try number 4 on your own. So start going through. You got to factor. You got to check for all kinds of stuff, don't you? All right. Go for it.